Okay. So, this will be the last two lectures, right. So, we will start with subsynchronous oscillations, right, and after this we will see that wind up and non wind up limiters, those things, and with this we will close this course. So, whatever we have seen previously, that we have considered that whole turbine, generator, all together it is combined a single mass, right, and we try to find out the oscillations with respect to other generators, but here we will do a little bit separately, and this is actually subsynchronous oscillations, right. So, sorry, in the analysis of power system dynamic performance so far, the rotor of a turbine generator, right, was assumed to be made up of a single mass that we have seen so far, right. We just consider that it is a single mass, I mean we combine together. Such a representation, it accounts for the oscillation of the entire turbine generator rotor with respect to other generators, right. The frequency of this mode of oscillation is usually in the range of 0.2 to 2 hertz, right. This we have also discussed before. Now, in reality, a steam turbine generator rotor has a very complex mechanical structures consisting of several predominant masses such as rotors of turbine sections, then generator rotor, couplings if it is there, right, then an exciter rotor, right. So, connected by shafts of finite stiffness. So, the stiffness of the shaft we will assume. Therefore, when the generator is perturbed, the torsional oscillation results between different sections of the turbine generator rotor, because in the your what you call turbine case, you have a high pressure portion of the turbine, low pressure also, intermediate pressure, low pressure, they may have different section, right. So, earlier whenever we have considered this, we consider this turbine generator as a combined mass, but here we will see it separately, right. So, the torsional oscillations in the subsynchronous range could under certain conditions interact with the electrical system in an adverse manner. So, the special problems related to the torsional oscillations include the following. Now, A, the torsional interaction with power system controls, subsynchronous resonance with series capacitor compensate transmission line, and torsional fatigue duty due to network switching, right. So, the torsional characteristic of hydro units are such that interaction with power system controls or transmission network has not been a source of concern, right. So, now turbine generator torsional characteristics, right. So, first is we have to see the shaft system model, because you have turbines, we have your what you call high pressure, intermediate pressure, low pressures, right, and that is also coupled with the generator. So, we have to see that how we can model it, and we will go for simplest model. So, the rotor of a thermal generating unit is a complex mechanical system. It may exceed 50 meters in total length and weight several hundred tons. I mean, I do not know whether you have seen the open rotor, particularly for thermal power plant or not. If you see that rotor thing, then you will find that your everything together, I mean it is very, rotor is very long, right, and your what you call, and it may exceed 50 meters in total length and weight may be several tons, because you have turbine, then generator is coupled, right. So, it is a very complex system and weight will be very heavy, right. The rotor contains your mechanical your machine shaft sections of varying sizes and couplings that are either integral or shrunk on and keyed to the rotor, right. The turbine sections contain discs, blades and other smaller components. So, the generator includes coil slots and retaining your what you call rings. Such a rotor system has a large number of torsional vibration modes both above and below the rated fixed frequency, right. So, the problem due to interaction between the electrical system and the rotor mechanical system is principally in the subsynchronous frequency range, right. So, these are the things, certain things studied by many researchers in the past, right, and only little bit we will study in this lecture. So, this allows the representation of the rotor system by a simple lumped mass model for electrical system interaction studies, right. So, now after this we will come to your what you call that your figure 1, that how we represent. For example, figure 1 I am coming. Figure 1, it shows the structure of a typical lumped mass model of a generating unit driven by a tandem compound reheat turbine. We have assumed that it is a tandem compound reheat turbine. The 5 torsional masses represent the rotors of the generator, 2 low pressure turbine sections and intermediate pressure, that is IP turbine section, and a high pressure turbine sections, right. So, the generating unit is assumed to have a static exciter, right. For a unit with a rotating exciter driven by the same shaft system, there will be an additional mass representing the exciter rotor, but we are assuming the static exciter system, right. Otherwise, if you assume a rotating exciter, then you have to what to call you have to represent it by an additional mass. So, that means we will come to say figure 1. So, it is a simple like your connecting one after another model. So, this is generator, is output torque is Te and it is marked as 1, and this is your low pressure turbine. There are say 2 sections of low pressure turbine, LPA and LPB, 2 sections are there say. So, this is your section 2 LPA and LPB, right, and here torque is TLPA, here TLPB, and then intermediate pressure, here it is marking as a section 4 and this is your TIP, right, all torque representation, and this is section HP high pressure portion, we are making numbering at 5 and this is your THP. Now, the stiffness of the shaft, right. So, it is 1 and 2 is connected, we are representing as a K12, right. Similarly, 2 to 3 we are representing as K23. Similarly, 3 to 4 we are representing as K34, and similarly 4 to 5 we are representing this as a K45. These are the stiffness of the shaft, right. We have to mathematically we have to relate this. So, this is actually high pressure, intermediate pressure, 2 low pressure sections, and this is the generator, and this is the structure of a typical lumped mass shaft system model. So, now nomenclature is here that THP, TIP, TLPA, TLPB, there is a mechanical torque developed by the respective turbine sections in per unit, right. T is the generator air gap torque in per unit, right. This all these things while studying synchronous machine, this T omega 0 all have been defined, right, and omega 0 is equal to rated speed in electrical radian per second is equal to 2 pi f 0, and it will be 377 radian per second if f 0 is equal to 60 hertz, right. And omega 0 m, that is your rated speed in mechanical radians per second, this we have seen before, that is 2 upon p f into omega 0, right. So, p f is the number of field poles. This we have seen when we are in the beginning, when we are studying your synchronous machine, right, and say omega I is equal to speed of mass I in electrical radian per second, right. So, and delta I actually angular position of mass I in electrical radians with respect to a synchronously rotating reference, right. That is, we can write delta I is equal to omega I t minus omega 0 t plus delta I 0. Delta I 0 is the initial angle, right, and omega 0 your what you call omega 0 it is rated speed in electrical radian per second, this is omega 0, right. So, it is minus omega 0 t and this is omega delta is equal to omega I t, right, and delta omega I is speed deviation of mass I in per unit, that is omega I minus omega 0 divided by omega 0, right. So, and d actually we call damping coefficient or factor in per unit torque per unit speed deviation. This we have also seen that d is the damping coefficient, right, and h is equal to your inertia constant in megawatt second upon MVA, that means h in second. This megawatt by MVA, it is a dimensionless, it is second, right, but we are writing megawatt second per MVA. So, h actually is your what you call that in second, right, and k is equal to shaft stiffness in per unit torque per electrical radian, right, and t we know that time in second, right. So, the shaft system dynamic characteristics are defined by 3 sets of parameters, right. That is your just hold on. So, 3 sets of parameters, that is your, this is one is inertia constant h, this is one of the individual masses, then torsional stiffness, your stiffness is k of the shaft, right, that is shaft different section 1 to 2, 2 to 3 we have given 1 to 2 k 1 2 in the figure 1, right, and connecting adjacent masses and the damping coefficient d, right. So, these are the actually what you call the 3 sets of parameters, we can define it by 3 sets of parameters. So, if it is so, then inertia constant h, right. So, this earlier we have seen that your what you call that your inertia constant h for synchronous machine modeling, when we are developing, we have already seen the inertia assigned to each rotor mass includes its share of shaft inertia. So, turbine blades are assumed to be rigidly connected to the rotor, right. Now, if the moment of inertia of a rotor mass is j kg per meter square, right, the per unit inertia constant h is given by this. Earlier we have derived this for synchronous machine chapter, right. So, h is equal to half into j into omega 0 m square divided by volt ampere base, right, and this one we can write half j in bracket 2 pi, that is your rpm, right, 2 pi r, that is per minute divided by 60 whole square divided by Va base, right. This already we have your what you call we have derived for your synchronous machine case the inertia, right. Now, next is the torsional stiffness k. For a shaft of uniform cross section undergoing elastic strain, the torsional stiffness or spring constant is given by, this is actually little bit from physics, right. So, its spring constant or your what you call or torsional stiffness, we k is equal to g into f upon L, directly we can write that, right, where g is equal to rigidity modulus of shaft material, f form factor which defines the your geometric property, and L is the length of the shaft. Therefore, k is equal to g f upon L, this is equation 1, right. Now, for a solid shaft of circular cross section say with diameter d, we can write this is your f, this is your f is equal to form factor which defines the geometric property. So, f is equal to actually pi d4 by 32, right. This is equation 2. The torsional stiffness defines the relationship between the torque transmitted and the angular twist between the two ends of the shaft, right. That means, we can write that in general that T is equal to k into theta, this way we can write, where T is equal to torque in Newton meter and theta is equal to twist, that is in radian, and k is equal to stiffness, that is Newton meter per radian. So, torque is equal to we can write k theta, right. So, in a turbine generator rotor, each shaft span consists of several sections of different diameters. The torsional stiffness of each section is determined and then a single equivalent stiffness is computed as follows. So, how we will do this, that 1 upon k total, that is the total stiffness, is equal to sigma 1 upon k individual section, that just you have to, this is the relationship, that 1 upon k total is equal to sigma 1 upon k individual section. For the representation of turbine generator shaft system in power system studies, angles are expressed in electrical radians or degrees, right, with the number of generator field poles equal to Pf, right. So, we know this relationship, you know, theta electrical is equal to your what you call theta mechanical into P by 2 general relationship we know. So, theta electrical radian is equal to theta mechanical into Pf by 2, Pf is the number of field poles, right, or we can write theta electrical is equal to Pf by 2 theta m, this relationship also we know, right. In system studies, torque is normally expressed in per unit with the base torque equal to. So, this base torque T base is equal to Va base upon omega 0 m, right. This This one we have already derived in your synchronous machine chapter, right? Sorry, synchronous machine, that your modeling, development of the modeling. So, this is VA base and omega 0 m and omega 0, the relationship also know, you substitute, it will be actually your PF, the VA base into PF upon 2 omega 0, right. So, that there your what you call this relationship, that your what you call this omega 0 m, that mechanical radian per second and electrical radian per second same. So, already we have made it. So, this omega 0 m we are replace it by your what you call that 1 upon omega 0 m replaced by Pf upon 2 omega 0. That means, this one we have already done it, no, that your I am making it here. Suppose this omega 0 m, whatever we are writing here, that is your just to this thing, that is your Pf divided by 2 omega 0. That means, omega 0 is right is equal to your what you call that omega 0 m into Pf by 2, right. So, we know theta e is equal to Pf by your what you call P by 2 into theta m. So, therefore, omega 0 is equal to omega 0 m into Pf by 2, that relationship we are using here, right. So, this is already this thing already we have derived in synchronous machine topic, right. So, the torsional stiffness is then given by that K, that is a torsional stiffness, it is per unit torque per electrical radian, right. So, in general it is a dimensionless quantity is equal to K, that is Newton meter per mechanical radian divided by Pf upon 2 into T base, right. This way we can represent, you can try also simple thing, right. So, it will be K, that you define the your unit, it is Newton meter per mechanical radian divided by Pf by 2 into torque base. So, if we substitute the torque base expression, so this will become actually K, that is your Newton meter per mechanical radian, that is that units also you are writing in the bracket for easy understanding, and then T base you replace, right. T base whatever you have got from here, T base you replace by this one, right. If you do so, then it will become K Newton meter per mechanical radian divided by VA base into 4 omega 0 upon Pf square, right. So, this is actually expression for K. Next is the damping coefficient. So, there are a number of your what you call sources contributing to the damping of torsional oscillations, right. So, number A, that is steam forces on turbine blades, right. That is because that steam actually you inject on the turbine blades. Therefore, the oscillation of the turbine blades in the steady state steam flow introduces damping, right. As an approximation, this may be represented as being proportional to the speed deviation of the respective turbine section, right. This is for the steam, your what you call, that is the steam forces on turbine blades, right. Now, second one B, that is a shaft material hysteresis. When the interconnecting shaft section twist, damping is introduced due to the mechanical hysteresis of the shaft material as it undergoes cyclic stress strain variations, right. So, this is number 2. Then number 3, the electrical sources, that is generator, exciter and transmission network contribute to damping of oscillations. Therefore, that your what you call that your there are number of sources contributing to damping. One is the steam forces on turbine blade, then B is that shaft material hysteresis, and C is last one is electrical sources. Electrical sources means generator, exciter and transmission networks contribute to damping of oscillation, right. So, damping levels associated with torsional oscillations are very small and are a function of the your what you call turbine generator output, right. So, time constant associated with the decay of torsional oscillations range from 4 to 30 seconds, right. So, these are the time constant associated with the decay of torsional oscillation, right. So, it range from 4 to 30 seconds. In this model, the of the shaft system will assume all sources of damping may be represented in terms of damping torques proportional to speed deviation of your individual masses, right. So, we will represent it in a simplest manner, that is damping torques between rotors are assumed to be negligible, right. So, now shaft system equations. Now, because shaft system we have seen, you have generator, you have a low pressure section of the turbines, then intermediate pressures, then high pressure, right. So, we will illustrate the development of equation of individual masses by considering the rotors of the generators and LPA turbines shown in figure 2, right. So, this is actually only we have considered whatever we have seen in figure 1, this is actually section 1, this is actually 1, right, and this is actually 2, only these two parts we have considered. Similarly, 3, 4 like this. So, this is actually inertia written is M, what we will take as a H1, right, and its damping for this section is D1. This is also instead of M2 we will take as a H2, right, and this is D2, and this is section 1 and this is section 2, right, and here that stiffness, that is K12, and this is the torque T12, right, acting on this shaft, and this is your omega 0, right, this is your omega 0, and this is actually omega 1. So, your what you call that deviation between omega 0 and omega 1, that is your delta 1. Omega 0 is the rated speed, right, that is the rated speed, but we are assuming that it cannot be on rated speed, maybe some your what you call, it is not ideal. So, some variation will be there. So, that is why this is your angle is delta 1. Similarly, if this is omega 0, this one your rated speed. So, for the your LPA, that is that low pressure, one of the low pressure section, this it is showing omega 2, right, and this is your delta 2. Although they are what you call, they are connected together, right, but shaft has different stiffness. So, naturally all this variation omega 1, omega 2 may be your what you call not your what you call not much difference, but some difference will be there, it cannot be neglected, right. And this is the electrical torque we have defined, and TLP also defined, and your T12, then section 2 to 3, where this is section 2, this side is section 3 is also connected, right, section 3 is also connected with this. So, that is why it is shown T to 3. So, this way only what we have done is we have only considered first section 1 and section 2, and this one again I am telling, this is actually H1 and this is actually H2, right. Instead of MEM we will write H, because throughout this course we have taken H, right. So, if you now write down the equation one after another, so from our your intuition we can write those equations, right. So, for example, the various components of torque associated with the generator rotor are as follows, that input torque T12 will be K12 delta 2 minus delta 1. So, this is input torque T12, I mean to that your generator side, right, input torque T12 will be your K12 the stiffness, right, into your delta 2 minus delta 1, that is the angle difference, this delta 2 minus delta 1, and that is your T12. So, this is their input torque, right. Similarly, output torque is equal to TE, this is my output torque, this is your TE, right. Now, damping torque is D1 into delta omega 1, right. So, this is actually D1 and it will be delta omega 1, right. So, later we will see this. So, accelerating torque, then TA will be equal to T12 minus TE minus D1 delta omega 1, right. So, this is how we write the acceleration torque TA is equal to, right. So, the equations of motion of the generator rotor then can be written as that 2H1 ddt delta omega 1 is equal to TA, that means for this part, that means this is my generator part, this is my generator part, right. So, this equation earlier also we have seen this, and 2H1 ddt of delta omega is equal to TA is equal to K12 delta 2 minus delta 1 minus T minus D1 delta omega 1, right. Similarly, for delta 1 ddt of delta 1, this equation we have already seen before, that for synchronous machine generator for single machine infinite bus system. So, there we wrote no ddt of delta is equal to delta omega into omega 0, but it is for generator section 1, that is the generator, that is why we write ddt of delta 1 is equal to delta omega 1 into omega 0, right. So, this part therefore, this part for this generator, right, for the generator. Now, the next one, similarly the following are the equations of the LPA turbine section. Now, input torque to the LPA section will be your, if you, this is the LPA section, it will be your TLPA plus T23, this is the input torque to this, right. Therefore, here it is your, here it is that input torque will be TLPA plus T23, right. So, T2 is equal to TLPA plus K23 delta 3 minus delta 2, because this side, although two sections are shown, right, then this is my section 1, this is my section 2, that other side also it is connected, no, just hold on, that section 3 also, that LPBB part is connected, right. So, this is the shaft. So, T23, so then here it is angle delta 2, for here also your this thing also it is omega 0, this angle is delta 3, right. So, that is why you are writing, and stiffness for this one, for this shaft it will be K23, that is why you are writing K23 into delta 3 minus delta 2. So, this is delta 3 minus delta 2. Similarly, for section 4, section 5, this way from your intuition or from the inspection you can write it, right. So, that is why we are writing this equation, that TLPA plus K23 delta 3 minus delta 2, right, that is the input torque. Now, output torque, that is T12, that for this section if you come for this part, in this case its output torque is T12, which is input to the generator, right. So, out T12 is equal to K12, then delta 2 minus delta 1. So, this output torque is that T12 is equal to K12 delta 2 minus delta 1, and damping torque is equal to same as before, for the section 2 it will be D2 into delta omega 2, right. Thank you very much, we will be back.